The first topic that we will cover with this class are integrals. So, first of all, well, this may be some sort of notation that you've seen in the past if you have been using integrals or studying integrals before. And the idea is, well, what they are, what does this notation mean, and then things that we will ask ourselves are, well, what are some properties of integrals and how do we compute them? So let's start. Suppose that I have some function f, and suppose that it is positive, just like in this graph here. I have some function f, which is always positive. And suppose that it is defined within some interval, a and b. So I'm only interested in the function in this interval a and b. Then the integral between a and b of the function fx is the area under the curve. So what the integral does is computing the size of this area, the one that is determined by a and b, the extreme of the intervals, the x-axis, and the function itself. So this is what we call an integral. So I'm integrating the function f between a and b, meaning I'm computing the area under the curve of the function f. Furthermore, we introduce this dx to specify that we are integrating with respect to the variable x. In general, for us, this will not be particularly important, but for example, later on it may become apparent why we also add this dx. So let's think a little bit of how would we compute the area under a curve. So let's think for a second that here I have this area that I want to compute, and let's think that, well, we can somehow approximate it. And let's approximate it by dividing the interval a, b in some smaller intervals, all of the same length. And suppose I have n smaller intervals. Now this size of the rectangle is going to be b minus a, which is the length of the interval, divided by n, the number of rectangles I consider. So if I want to compute the area of any of these rectangles, what I need to do is to multiply the size of one, or the length of this side, times the length of this side. The length of this side is b minus a divided by n, because they are all of the same length. And then the height of the rectangle is the value of the function at some point here within the rectangle. One thing we can note that we could notice, we don't care about it, is, well, if I were to choose, for example, the height of the function on the left hand side or the right hand side or the middle point, it doesn't matter. It all gives in the end the same result. So one way to compute the area under this curve is by dividing the space into smaller intervals and compute the area of each of these rectangles, and then summing these areas together. And this is what this formula does. Now we can think of computing an integral being the same as making these rectangles as small as possible. So if I decrease these rectangles, okay, the length of these rectangles, meaning that I'm actually adding more and more rectangles of which I'm computing the area, that is what the integral actually does. So we can sort of approximate it by selecting n rectangles, And as I make this n goes to infinity, then I'm actually computing the integral of the function. So in our initial definition, we consider f to be a positive function. Suppose now it is any function. Then what the integral is, it computes the areas that are over the x-axis, so the positive parts of the function, and it also computes the areas of the regions that are below. And the integral returns the sum of the areas over the x-axis minus the area of the regions below of the x-axis. Okay? Okay. Some properties. Now the first three properties are all about how we can divide the space where we are integrating into different regions. So suppose that I'm computing the integral of some function f in an interval ab. Suppose that c is a point between a and b. Then I can basically split the computation of the integrals into the integral from a to c and the integral from c to b. What does that mean? Let's look here. Suppose I have c somewhere here, then I could divide this area into two sides, and this would be the integral of the first part plus the integral of the second part, which makes sense. The second and the third property basically are telling us the exact same thing, that if I compute an integral from a to a, the integral is 0. Why is that? So if I compute the area from a to a, it means that this side of, well, the approximating rectangle is equal to 0. So that the size of this area must be 0. Second sets of properties that I want to highlight are basically sums and multiplication by constants. So integrals with this behave as we would expect, meaning that the integral of the sum of two functions is the sum of the integrals of the individual functions, and the integral of a constant multiplied by a function is equal to the constant times the integral of the function. So this is why, well, these are the properties that we have seen. They hold for matrices, they hold for derivatives, so this is really nice and simple. However, notice that here there is no property concerning the product of two functions. The integral of a product. I don't have any formula for it. Remember that although a little bit more complicated, we had a way to compute the derivative of a product of functions. Conversely, there is no formula to compute the integral of a product of functions. And this is why it is particularly difficult to actually compute integrals in practice. Okay? So let's take a little bit of a break from integrals. Everything will sort of tie up together just in a few slides. But let's define the idea of primitive of a function. So the function big F is called primitive of f if the derivative of big F is small f. So if I compute the derivative of the function big F, and this is equal to small f, then we say that big F is the primitive of small f. So computing the primitive is somehow the inverse process of computing a derivative, okay? So when I compute the derivative, I have a function and I go to its derivative. When I compute the primitive, I find the function such that if I compute the derivative of that function, I find my original function small f. So we will see that there are some basic functions where we are actually able to find the derivative, to find the primitive, actually, sorry, I apologize for this typo. So we can find primitives for some very simple functions, but in general, as I was saying, it is very hard to compute integrals or to find primitives, okay? So here I give you some examples that are in the slides, are in the lecture notes, and that I encourage you to look at. So, but one thing I want to highlight from these examples is, as you will see, we always say a primitive of. On the other end, when we compute derivative, we say the derivative of the function f is something. On the other hand, in all these examples that you read, we say a primitive of. Why? Because if some function big f of x is a primitive of small f, then also big F plus k is. Why? If I compute the derivative of this term here, then this k, the derivative of that is 0, and therefore I still find small f. So for each function, there are actually an infinite number of primitives, and they are all equal up to some constant, small k. So what we call the indefinite integral of a function, small f, allows us to find some primitives. So let's define as the integral from a to x of the function f a primitive of the function. Now notice that here one of the extremes of integration is the variable x itself. That allows us to find primitives. So if I am able to compute an integral, okay, then I'm able to find a primitive by using what I call an indefinite integral, meaning an integral where the variable x is one of the extremes of integration. Now here there's another explanation of why there is an infinite number of primitives. I'm not going to go through that, but you can find it in the lecture notes. So actually this result that we discussed is called the fundamental theorem of calculus. So sort of the name already tells you about its importance in calculus. And so this theorem indeed tells us that if we are able to compute the integral of a function, and we define the indefinite integral where the extremes of integration are some number a and the actual unknown x, then I'm able to compute a primitive of the function small f. So in particular, one more thing that sort of a corollary of this result is that if I compute the integral of a function f between two values a and b, then this is actually equal to the primitive f evaluated at the point b minus the primitive of f, big F, evaluated at the point a. Let's see an example here, okay? So I want to compute the integral of cosine of x between 0 and pi over 2. Now in the previous examples, we deduced that the a primitive of cosine is sine. Why is that? Because if I computed the derivative of sine, then that's cosine. So in particular, since sine is a primitive, then the integral between 0 and pi over 2 of cosine is sine evaluated at pi over 2 minus sine evaluated at 0. Now, it doesn't matter if you remember this or not, one can show that the sine at pi over 2 is 1 and sine at 0 is 0, and so the value of this integral is indeed 1. There is another example that you can look at if you think it may be useful. Now, the very last thing that I want to mention is, so in the exercises that you may find, or some of the simplest questions that, some of the questions that I may ask you in a quiz, I may ask you to compute integrals or of some very simple functions. Because in general it is extremely hard to compute integrals of generic functions. There are no formal, well, there are some rules, but basically it's not that you see a function and you know how that function is constructed, as for example in a derivative, and then you just apply the rules. Computing integrals, it's a little bit more of an art, because you need to decide which method may work best in different setup. So it is actually also difficult to implement software that computes integrals for you. So actually in practice or in a computer, how integrals are evaluated is by numerical approximations of the form we saw by dividing the area into rectangles. So there are many routines that are implemented that approximate the value of the integral, since it's extremely difficult to actually compute it analytically. So this is just one of the libraries that, for example, you may find in Python, which has many approximation rules to compute integrals. So this was just a very brief overview of integrals that I hope